Let's look at the math, that is the formula for our critical velocity. So we happen to understand critical velocity this way. It's defined as specific velocity at which the fluid moves from being laminar to turbulent, right? And we happen to see this as well. So if it's less, then we are looking at streamline. If it's more, it's turbulent. And now we're looking at the math. So exactly what is it dependent on? So we are taking up a very particular scenario. We have fluid through a pipe, basically. Okay. Again, there are a lot of different scenarios, infinite possibilities are there. We're just taking up the starting point. The most simplest point is picking up a pipe and making the liquid flow, the fluid flow. So now factors that influence critical velocity. How sticky the fluid is, first thing, right? Example, honey will not flow the same way as water. Diameter of the pipe. So if you have a very thick pipe, then it being turbulent, the chances is high. And if it's a thin pipe, then you guys have seen water show. So when they use thin pipe for a laminar flow. Okay. So it plays a role, diameter plays a role, density of the liquid plays a role. Okay, so with all of this, we have to figure out, with all of these commonsensical points, we have to figure out now the formula. How do we do it? We're going to make use of dimensions. Okay, so we are using dimension analysis, guys. Right? So what we're looking at is your critical velocity is proportional to the stickiness, the density, and your diameter of the pipe. Okay. Now, what is the dimension at the LHS? So we are looking at L t minus 1 and yeah, M is 0. Then on the RHS, what do we have? We have the stickiness. So this we need to know, ML minus 1, T minus 1. And we have the density, which is, right? That's density. This you guys know. And you have the diameter, which is L to the power of 1. Now, let's substitute all of this into 1. Substituting above in 1. So what we have here is L1 T minus 1 M naught is equal to M L1 T1 to the power of A times of ML3 V times of L to the power of C. Okay, so when you compare and solve it and all that, so on comparing, you will get equations, for example. So when you take up M, right? Powers of M. So on the left hand side, we have 0. You have A plus B. Okay, yes, I'm looking at power MA, MB. So A plus B. That's the total power. I'm just using simple set of exponent formulas. And powers of L. So L will be 1 is equal to minus A minus 3B plus C. And powers of T. So we are looking at -1 minus A T, right? That's it. Okay, we got the value for A. So from solving this, what do you get? A is 1, B will be -1, right? And C will be, so if this is 1, this is -1, this will be 2, and if I send it across, it will be -1. And of course, this will reflect our commonsensical point that it is proportional to rho and D. It has to be so. What did you start with? Yeah. So critical velocity is directly proportional to your stickiness. That makes sense. More the sticky, it will tend not to change how it's moving basically, right? More the stickier it is, more laminar it would be. Density, of course, if it gets thicker and heavier per se, then the critical velocity decreases. And of course, diameter. This you guys can see. Diameter of the pipe. If you take a thick pipe, then obviously it will lead to turbulence. Do you guys agree? Then finally, I have the proportionality constant K. So when we deal with K, what we're looking at is it's a dimensionless constant, obviously, because the dimension is taken care of by the other variables. So here K is dimensionless. That's one thing we can be sure of. This is found experimentally. Okay. And for this specific scenario, for this case, so for this specific scenario, we have, so what we are looking at is for a specific scenario or specific scenario. Okay, I'll mention the scenario. Flow of fluid, a cylindrical pipe. So dimensionless proportionality constant, your K. We can, this is of course experimentally determined. This will be equal to something called as, this is critical. So this way actually we'll be seeing this as well. Number. So R, I forgot the presentation, guys. Let me take a second. I think it's this. Yeah, right. We have RE and C subscript. Okay. So very simple derivation. So what we're looking at is the idea of critical velocity. So we have seen this laminar to critical velocity. What do we have? Laminar is a steady flow, and post critical velocity, somewhere along here we get to see the critical velocity, and it becomes turbulent. Okay, not exactly, but point is, it's a transition from here to there, right? So critical velocity is that velocity wherein we transition from being laminar to turbulent. Like if you open a pipe, when when we have a steady stream, and you get to see that it continues to flow. So if there's no other disturbance per se. So if there is a disturbance, what happens? It moves from being, or need not be that disturbance itself. If you have, there's so many variables, if any one of them change, there's a possibility that you will move from laminar to turbulent. So what are those factors? That's what we looked at. We use dimensional analysis. So it's commonsensical for us to understand, or experimentally we can see that the stickiness, the density, and the diameter of the pipe. So in this case, we're looking at water flowing through a pipe. So when they vary, any one of this varies, we get to see change in critical velocity. So with that understanding, we went on to use dimension analysis, and we found the value of A, B, and C. And it reflects our commonsensical stuff. Of course, when we have proportional symbol, when we remove it, we get a constant, and that is, of course, in this case, it has to be dimensionless. It's found through experiment. I have given you guys a specific scenario. You just have to know this. So this scenario, we have critical, the name given to the K, or the value of K, is equal to critical Reynolds number. Sorry, I think I said Raymond's number. It's a Reynolds number. So that is it. So you guys are over here. And then we have this.